really exciting to kick off the Stanford's new academic year's HAI seminar. For those of you who are joining us for the first time, HAI is a relatively newly established institute at Stanford for human-centered artificial intelligence. My name is Fei Li. I'm a professor at Computer Science Department and also co-director of HAI with Professor John H. And just very exciting that joining us today for the first kickoff seminar is one of the world's most famous, renowned, and also beloved member of Stanford AI community, Dr. Andrew Ng. Before I give a brief introduction about Andrew, let me just say a couple of words about HAI. HAI is an institute whose mission is to advance AI research, education, policy, and outreach to better human conditions. We are a highly interdisciplinary institute here at Stanford that works on very advancing AI technology, as well as many of the social and human issues related to AI, whether it's fairness and bias, ethics, future of work, geopolitics, and we work with important professional schools at Stanford, such as School of Education, business, medicine, and all across the campus. So for those of you who are part of the community, we really invite you to join us in any way, whether you're students, a researcher, or faculty, or just alum. For those of you who are joining us around the world, we welcome you to sign up to our mailing list, to our events list. We hold a lot of exciting events, and our weekly seminar is intended to bring you the latest thinkings by AI scholars and thought leaders who are at the forefront of making changes in AI. So like I said, what an honor to introduce Andrew, who has been a long-term friend for more than a decade. It speaks of our age, Andrew. Andrew is literally the first person I met when I joined Stanford. And he's the founder and CEO of Landing AI, also founder of deeplearning.ai, and co-chairman and co-founder of Coursera. All of these entities are changing the world as we speak. I can't imagine a person does all of them. And is currently also an adjunct professor at Stanford University. He was a chief scientist at Baidu and part of the leading team of Google Brain project many years ago when it was just starting. And you know, Andrew will share with us his topic of bridging AI's proof of concept to production gap. And before we start our session today, I just want to introduce also a really important colleague of mine whom you'll become very familiar with as the academic year goes. And this is our new director of research at HAI, Dr. Deep Ganguly. And he'll be sharing a few house rules with everybody. Thank you, and thank you, Andrew, for joining us. It's I'll be very listening to your talk attentively.
Yeah, thank you, Fei.
Thank you, Fei. And then before we kick off, just a few house rules. So first, thanks everyone for tuning in today. I'll be moderating the question and answer session at the end of Andrew's talk. So to submit a question, please use the Slido website. There's a link in the chat box of the Zoom, and you can also point your phone at that QR code, or you can go to our events website at hai.stanford.edu/events and click join the conversation. And without further ado, Andrew, please take it away.
Thank you. Thanks, Steve, and thanks, Feifei. Yeah, it was surprising when Feifei mentioned that HAI is a relatively new institute, because I think thanks to her leadership and John Eschmandy's leadership at Stanford in the AI world, it feels like it's already a major institution. So it's interesting to be reminded that despite HAI's presence and all of these wonderful events I see across the campus, the virtual campus all the time from HAI, it's interesting to be reminded that it's just is even just in the early days. So it's nice to see everyone here. Last night when I was looking at the attendees list, I noticed that all of you watching this is a very diverse audience. I counted 23 CEOs on the attendee list. There are a few dozen professors, a few hundred students, also a few hundred machine learning engineers and machine learning researchers, and one person in the registration form listed themselves as a poet. So whatever you are, CEO, professor, students, machine learning engineer, researcher, or poet, I'm really glad to see you here today, and thank you for joining us. What I hope to do is share with you a perspective on one of the challenges facing AI. AI has created a ton of value, but a challenge and almost a bottleneck or barrier for it to create even more challenge, more value. And this is something I see in multiple universities, companies, industries, is bridging the proof of concept to production gap. So let me share my slides. And what I hope to do today is share with you a perspective on this proof of concept to production gap, as well as what all of us in academia or in business or maybe even, actually I saw a few government leaders as well, may be able to do to overcome some of these challenges so that AI can become even more useful. So I've been saying for, I think, about 5 years now that AI is the new electricity. Similar to the rise of electricity, about 100 years ago, AI is poised to transform every industry. But what have we really done? I think AI has already transformed the software industry, especially the consumer internet industry. We've transformed, we as a community, we've collectively transformed web search, online advertising, machine translation, social media, a lot of great things, also some problematic things. But the software internet tech industry has many teams that know how to use AI well. There's still a lot more work to be done, but it's clear it's created tremendous value. Once you look outside the software industry, I think AI's impact is still modest and growing. But I think that looking into the future, the impact of AI outside the software industry will be even bigger than its impact on the software industry. But the way we build and deploy AI systems in all of these other industries will have to change a bit in order to make them more effective. Now, given how diverse today's audience is, I want to take one slide to just say what I mean by AI. So AI means a lot of things these days, but as some of you will know, 99% of the value created by today's AI technology is through one idea, which is called supervised learning, in which we learn input-output mapping. So input an email and output is this spam or not, that's your spam filter. Or input an audio clip and output a text transcript, that's speech recognition, powering voice search, powering the smart speakers you may have in your homes. Most lucrative application of this is probably online advertising, not the most inspiring application, but certainly very lucrative for some large online ad platforms, in which you have an AI system that inputs an ad and some information about you and tries to figure out if you click on the ad or not, because showing slightly more relevant ads has a very direct impact on the bottom line of the large online ad platforms. Some work that my team at Landing AI has been doing is visual inspection, where we'll take as input a picture of a manufactured object, say a picture of a phone, and we try to tell if this object that's been manufactured is scratched or dented or has some other defect. Or medical imaging. At my Stanford group does a lot of work on where we input, say, a chest X-ray image and output, do we think this patient has a pneumonia or some other condition? So the AI world has generated a lot of amazing research progress, a lot of amazing proof of concepts in the business world as well. For example, This is one result that my collaborators and I had announced some time back. This is with Pranav Rajperkar, Jeremy Irvin, Matt Lundgren, Kurt Langlos, Perfect Patel, and many others. Chest X-rays is one of the most commonly done medical procedures. We use it to help diagnose pneumonia, lung cancer, also COVID. So there are about 2 billion chest X-ray procedures per year worldwide. And so we announced a result where we claimed that deep learning achieved radiologist level performance on 11 pathologies and did not achieve radiologist performance on 3 pathologies. And many groups have announced results of this flavor, right? Faith-based groups published wonderful papers of this flavor. Other groups at Stanford, Sebastian Struen's group, diagnosing skin cancer, and just many groups around the world have published results like this, saying that AI does as well as a human doctor on diagnosing something from some type of medical modality. So given all of this amazing research progress and these amazing proof of concepts, why aren't these systems widely deployed to hospitals yet? If you were to get a chest X-ray today, in most countries, certainly in the United States, but in most countries, actually in all countries, is very unlikely that there's an AI system reading your chest X-ray. So why is that? If there are research papers, they're peer-reviewed, and that I will stand behind my papers, saying that supposedly they outperform even board-certified Stanford radiologists. So what I see across the AI world is that there are many research studies or proof of concepts. These are the things that works well on a researcher's laptop running in a Jupyter notebook, but that still needs to bridge that proof of concept to production gap. So what I hope to do today is share with you 3 of, I think, the top challenges in bridging the proof of concept to production gap, in the hope that wherever you are, whether you're in academia or business or for-profit, non-profit government or governments, that if you have an exciting AI idea, if you can help your team get to proof of concept, that's wonderful. That should totally be celebrated. But watching out for some of these challenges, I hope will also help more AI projects get into practical deployments. So I think 3 of the top challenges in bridging the proof of concept production gap are challenges of small data, of generalizability and robustness, and of change management. So let me go over these 3 and then also talk a bit about the full cycle of machine learning projects, which I think will help all of us as a community take more AI projects to successful production deployments. So let's start with small data. A lot of AI had grown up in consumer internet companies, right? The very large tech companies that have hundreds of millions or billions of users. And when you have that many users, you have big data. So I find that a lot of AI philosophies and tools and approaches were tuned to big data, given the nature of the companies in which AI had grown up. But a lot of industries have much smaller data sets. And for AI to be useful in those industries, we have to have better small data algorithm. For example, take visual inspection of smartphones, the example that I alluded to earlier. If you have 1 million pictures of scratched smartphones, then today there are, at least dozens, maybe hundreds of teams that can build a neural network to diagnose if there's a scratch, if a phone is scratched. And in fact, really building on Feifei's can't be emphasized more, similar work on ImageNet, all of that open source work, right, that people built on top of, many of those models will work well for the very important big data problems. But if but fortunately, no factory has manufactured 1 million scratched smartphones, which would therefore have to be thrown away. And the question is, given only 100 pictures of scratched smartphones, which may be all the data that exists, are you able to build a accurate inspection system? And this is critical for breaking open these applications of machine learning in visual inspection, where only small data sets exist. To dive more deeply into small data, here's another example. So the result I mentioned just now was, I said deep learning achieved radiology performance on 11 pathologies and did not on 3 pathologies. Well, these are the 14 pathologies. You can focus just on the first and the last column. The middle 2 columns has accuracy and confidence intervals. But let's dive into a few of these rows. So for the condition of effusion, we have a lot of data. We have 11,000 examples. And so there, a deep learning algorithm was able to diagnose at a level of accuracy that was statistically indistinguishable from a radiologist. But if we look at a rarer condition like hernia, where we have about 100 examples, there radiologists still outperform the learning algorithm. So it turns out that learning algorithms work well on data sets where the distribution is like that on the left. If you have 1,000 examples of every class, then it's not easy, but it is relatively easier to get a learning algorithm to do well on all of the classes. But it doesn't do as well when your data distribution looks like that on the right, which is what we actually face in the medical domain. And I've been in a lot of conversations. Actually, I've listened in on a lot of conversations between a machine learning engineer and a product leader or business leader or hospital leader. And the conversation goes like this. The machine learning person will go, oh, look, I have achieved very high accuracy on the test set. And it's a fair test set that I haven't looked at, the peaks is a fair test set evaluation. And then the hospital leader or the doctor or the business leader, the product leader says, congratulations on your high test set result and on your research paper publication, but your system just doesn't work. And the machine learning researcher or the machine learning engineer says, yes, but I do really well on the test set. And the conversation kind of ends there, unfortunately. So I think our job as machine learning researchers and engineers and developers is not just to do on the test set, is to solve the problem that actually matters for the use case we want to address. And I find that common metrics such as average accuracy do not reflect these small data occurrences problems. So for example, if your data distribution looks like that on the right, it's completely fine to ignore the hernia condition. Just never predict hernia, and your accuracy is just fine because hernias are so rare. But for practical applications, it's probably medically unacceptable to deploy a system that misses completely obvious cases of hernia. And so even though hernia is very rare and on an average accuracy standpoint is quote less important, for the practical hospital need, and my teams work with a few hospitals, so we're on the ground doing some of this work, is important to address these rare cases as well. So I think both on the I think fortunately I think that the research community and the business community is making progress on better algorithms for handling small data. For example, I'm excited about synthetic data generation using GANs were created by my former student, Ian Goodfellow, who was actually a Stanford student way back. But with GANs, this is actually an example in visual inspection, generating scratches of cars using GANs. So you don't need a million scratch cars to learn to detect scratches. You can synthesize scratches that actually I can't tell a synthetic scratch from a real scratch. And exciting research progress also on one-shot learning and few-shot learning, where algorithms are able to learn from very few training examples. And I think GPT-3 released just a couple months ago, just quite recently, was a very exciting step to a one-shot learning, few-shot learning in the language domain. I'm excited about self-supervised learning and self-taught learning, where we learn from large amounts of unlabeled data to do a labeled task, transfer learning and anomaly detection. But I think all of these are technologies that I think are exciting to help us overcome the small data challenges that are much more pervasive once you go outside your software consumer internet. Other than small data, a second challenge in bridging the proof of concept to production gap is generalizability and robustness. So going back to the AI, deep learning for X-ray diagnosis example, it turns out, those of us that work a lot in research and also production settings will know this. A model that works well according to the published paper often doesn't work in a production setting. So for example, when we collected data from Stanford Hospital, Stanford has a relatively modern X-ray machines and very well-trained technicians. So we collect images there. And when we train and test on images collected from Stanford Hospital, we can publish papers that are peer-reviewed and that will stand behind, showing that we can outperform human radiologists when we train and test on data from the same hospital. But it turns out if you take this model and walk it down the street, maybe to a hospital using older X-ray machines, and where the imaging technician, where the X-ray technician uses a slightly different imaging protocol. So maybe the patients are tilted at a slight angle, then the performance degrades. And this is in contrast to the performance of any human radiologist that would be able to walk down the street from Stanford Hospital to this other hospital and do just fine. So there is a huge gap between what works in a research lab versus what will work in production. And this is true not just for healthcare. This is true for many other industries as well. And so I think one thing that we should work on, both from the research and on the practical engineering side, is better tools and processes to make sure our algorithms generalize to different data sets than those trained on. I'll share a few more thoughts on this when I talk about the full cycle of machine learning projects. Finally, change management. When AI technology can take a workflow and automate part of it, and that can transform the work of a lot of people around it. And I think we need to get better at managing that overall change. So here's an example. This is some work I did with Anand Avanti, Nigam Shah, and Ken Jung, and others on palliative care. So palliative care, which is roughly end-of-life care, helps patients with terminal illness enjoy a high quality of life. We know that here in the United States, doctors in general make fewer palliative care referrals than we would like. I think doctors are good people. Many doctors want to keep fighting for the patient because they care so deeply about the patient. And my father's a doctor, and I know it's actually hard for a doctor to give up, right? You just want to keep fighting for the patient, which is a great attitude we want our doctors to have. But we know across the country that doctors make fewer palliative care referrals than one might wish. Now, there is in many hospitals, including Stanford Hospital, there's a specialized palliative care unit. Those palliative care doctors could proactively reach out, but the volume of patients makes chart reviewing patient records infeasible. So what we did was we built a learning algorithm to predict the chance of mortality of a patient over the next 3 to 12 months. And this recommends patients for consideration for palliative care. So this is the workflow that we actually built. This is a picture of Dr. Stephanie Harmon, head of palliative care at Stanford Hospital. And the data is made up for student privacy, but this is actually pretty much what she was seeing every morning. But so Dr. Harmon will wake up in the morning and pull up a table from the database, which looks pretty much like this, where she would see patient IDs, age of the patient, and the learning algorithm's estimated probability of mortality. This allows her to decide what patient charts to review in greater detail and what doctors to call up to recommend for consideration their patients for palliative care, or to make sure that the advanced care directive is taken care of, for example. So what do you think happened when we first rolled out the system, right? When a doctor calls up another doctor and says, hey, I think your patient is at high risk of mortality, what do you think happens? Well, maybe not surprisingly, the doctor on the receiving end of the phone call goes, who are you? And who are you to tell me that my patient is at high risk of mortality? So what we realized was that we had to perform the change management process better because a system like palliative care affects a lot of stakeholders. It affects doctors, affects nurses, affects hospital administration, insurance, outpatient services, and of course, most importantly of all, it affects the patient. And so I feel like in a lot of projects I work on, I've learned over and over to go through the appropriate change management process. Because when we take a hospital's workflow and automate just a piece of it, be it reading x-rays or making palliative care predictions or something else, it disrupts or transforms the work of so many people around it that, budgeting enough time, identify stakeholders, provide reassurance, explain what's happening, right size first project, all of these things are important for us as technologists and or business leaders or academic researchers, if we want to play a role in making sure our amazing technologies go out there to have an impact. And I just mentioned key technical tools for managing change are explainable AI and auditing. And I just go shout, I think Fei Fei and HAI have been real thought leaders in helping advance the conversation on both of these important topics. I know that there's some AI leaders that think explainable AI is not important, that you train a black box deep learning, why do you care if you explain or not? And I actually personally just don't agree with that. And maybe a quick story. When we started, but explainable AI is actually complicated. So one quick story of where I got it wrong. When we built the first palliative care system and we started to show it to some doctors, the doctor's feedback was, hey, how can your learning algorithm possibly tell me that this patient has a 78% chance of dying in the next 3 to 12 months? Like, how could I possibly trust your AI system? And so we actually built on an Avanti, actually built a system using an algorithm similar to Lime, if the technologists have heard of it. We try to generate an explanation for the doctor that says, we think this patient is a high risk of mortality because looking at the health record, the EHR, the electronic health record, they received this diagnosis and they went this test. So this is why we think this patient is at high risk of mortality. And guess what happened? Doctors looked at it. They looked at a small handful of patients, looked at the explanations we generated, and they go, oh, got it. And then they never looked at the explanations again. And the lesson I learned was the doctors didn't actually need us to explain to them why a patient is at high risk of mortality. They're completely qualified to look at the EHR and judge for themselves as a patient is at high or low risk of mortality. What they actually wanted was some reassurance that our machine learning algorithm, that our AI system was generating reasonable conclusions. So what they wanted was just enough of an explanation for them to feel like our system was being reasonable. And once they had that level of comfort, they didn't care about our explanations anymore. They just didn't want to look at it anymore. And they would just look at our recommendations, use our system for screening, but then look at the patient charts, patient records themselves in order to decide what they wanted to do. So I think one of the reasons explainable AI is so complicated is because I think our field keeps on confusing who is this for? Are you trying to generate explanation for the doctor or for the patient or for a regulator or for someone else? And also, what is the action you want them to take? Do you need them to do something on a patient-by-patient basis, or do you want them to just be generally comfortable? Or do you want a regulator to help you spot if there's a major flaw? So I think explainable AI is important, and I think that and I think auditing as well. Face recognition today is a technology that seems highly problematic, and I think, given where we are, I think society will have a hard time trusting many face recognition systems, certainly here in the United States, unless we have some fair third-party audit to reassure us that they're doing the right things. So these are important technical things for us to work on to then bring it into part of the overall change management. Now, so I talked about 3 major issues, and what I think machine learning should do is start to be better at thinking systematically about the full cycle of machine learning projects. And so here's what I mean. We've been celebrating a lot the development of better machine learning algorithms. And when a team develops a successful research paper or proof of concept, it's wonderful, celebrate that. This is a phenomenal progress. And the progress, the work needed to actually take a system to production is even much bigger than that. There's all this stuff that needs to be done. And so I think and there's actually a very influential paper out of Google titled the High Interest Credit Card of Technical Debt. Messing up the title. Technical Debt in Machine Learning, High Interest Credit Card something. Apologies for messing up the title. It's a very influential paper out of Google several years ago. They talked about this. And I think in addition to building the machine learning model, all this other stuff is something that I hope we can become more systematic at. Now, when I talk about these things, some people ask me, is this engineering or is it research? And I think it can be either. I remember when a decade ago, leading researchers were telling me that they thought neural networks weren't scientific. They're leading researchers in computer vision, not Fei, other leading researchers in computer vision, they're telling me neural networks aren't scientific. And one she said, hey, Andrew, get real. Like, why are you just messing around with figuring out neurons? It didn't feel scientific to them at the time. And I think someone I'll talk about today will feel like engineering, but I think both the engineering community and the research community can do a lot to make AI engineering much more repeatable and systematic. So this is what I think of as some of the major phases of an AI project. You know, we have to scope the project, decide what problem to solve, acquire data, uh, carry out the modeling, right? Build the model, and then take it to deployment. And what I want to do is go backwards and run through these 4 major phases and very quick, share some quick lessons learned from each of these. So let's start with deployment. They'll go back to modeling, data, and scoping. So deployments. After you train a machine learning model, we still need to build a cloud or edge implementation and build monitoring tools. And I think the business world, we're getting better at how to deploy these systems to production. So for example, one design pattern I often use is so-called shadow deployment, where we may, for example, deploy an X-ray diagnosis system, but not use it to make any decisions, but just shadow a doctor, right? So this is safe because it's not doing anything. It's just shadowing doctor. And this gives us time to monitor the performance of the system and make sure it's making reasonable predictions, reasonable diagnoses, before we then allow it to play a role in making recommendations. Canary deployments is another common design pattern where we roll out to a small subset of users to monitor it for, to make sure the data distribution hasn't changed. And only after doing this do we ramp up deployment. So I find that right now, a lot of this work is done by engineering teams, but more systematic tools as well as research to help make this whole process more systematic, I think will make the deployment process more repeatable and reliable. And of course, we also need long-term monitoring and maintenance. So one thing I'm trying to do in the educational context as well is, I think we've done a lot, right? You know, at Stanford, at deeplearning.ai, really around the world, many institutions, many universities, many courses, to teach people how to build models. I think we still should teach more people how to go through this deployment process so that we can have more highly qualified machine learning engineers. Going backwards, let's talk about the modeling process. So it turns out that I find that building machine learning models is a highly iterative process. It feels to me much more like debugging software than developing software. So this is an iterative cycle, right? You come up with an idea for an AI architecture, and then you will code it up and train the model, and then it never works the first time. And so you analyze the result. I remember some time back, I trained a softmax regression model on my laptop. There was a small experiment around, so it was small, so I didn't need GPU or anything. Booted up Jupyter Notebooks on my Mac laptop, actually the same laptop that I'm using to speak with you via Zoom right now. Coded up simple softmax regression, data cleaning, all in Jupyter Notebook, trained softmax model, and then it worked the first time. And I still remember to this day my personal sense of surprise. It was like, I just couldn't believe it. Wow, I trained the model, it worked the first time. Like, never happens. And then I actually spent several hours debugging it because I just didn't believe it. It turned out it actually was working. But in machine learning, it almost never works the first time. And so a lot of the loop is carrying out analysis to figure out what's wrong with the model so that we can change the algorithm, data architecture, or what have you. And you go around this loop. And I find that in engineering execution machine learning projects, from the way we carry out sprint planning, if you're using agile development process, a lot of this iterative loop feels more like debugging. Hopefully that guidance will be helpful to some of the managers of machine learning projects. And if you look at the way we develop learning algorithms, today a machine learning model has 3 major inputs. You need the training data, you need to choose your algorithm, the neural network architecture or whatever, the piece of code, and you have the choice of hyperparameters. And so when building research results, we often download the standardized training data or test, dev set, test set, benchmark, and then you feed all these to train a machine learning model. when doing research, we tend to keep the training data fixed and vary the neural network architecture and vary the hyperparameters. And we do that so that different algorithms can be compared to each other on a one-to-one basis. But I find that in a modeling production setting, I often find myself holding the algorithm fixed, often holding the hyperparameter fixed, and just varying the training data. So one example, and actually I've actually given direction to my teams where I'll tell the teams, hey everyone, the algorithm is good enough. Please just use RetinaNet and please don't change the algorithm. Let's just keep changing the training data in order to make the algorithm work well. Maybe one example, when I was working on speech recognition, we did a lot of work on the speech model, but eventually I thought, all right, this algorithm is good enough. The algorithm, the code works, hyperparameters, spend a little bit of time tuning it, but our daily workflow was we will look at the speech recognition system's output and do error analysis. We'll figure out, oh, our speech recognition system has a really hard time listening to people with a certain accent, right? I was born in the UK, so just as a hypothetical example, let's say our algorithm has a really hard time with people with a British accent, right? That wasn't what we saw, but let's just say British accent since I was born in the UK. And then we'll say, great, let's go and get some more British accented training data. And that was actually the iteration loop. We'll keep on shifting the training data in order to improve the machine learning model's performance. And that keeping the algorithm fixed and varying the training data was really, in my view, the most efficient way to build this system. Now, I know some of you, I know that a lot of professors and researchers on the call, some of you are saying, hey, Andrew, is this research is engineering? And I'll say, I actually don't know. I think it's both, but I think the research community can do a lot to help make this process much more systematic as well. All right, working backwards. So talk about deployment, modeling, data. How do we acquire data for the model? In a corporate setting, I've seen, I sometimes, I've met, actually, I think there are 23 CEOs that signed up for this. So sometimes I talk to the CEO and they'll say, hey, Andrew, give me 2 years or 3 years to let my IT get into shape, then we'll have this wonderful data, then we'll do AI on top of that. And I think that's almost always a terrible idea. You should almost always, often most companies have enough data to start getting going. And it's only by building a system that you can then figure out how to build out your IT infrastructure, because there's so much data you can collect. Do you want more user data, more clickstream data? What data do you want? It's often by starting to build an AI system that you can then work backwards to help decide what additional data to collect. And one other aspect that I think is underappreciated in terms of thinking about the full cycle machine learning is deciding on clear data definitions. So here's an example I got from my friend Kian Katan-Furush that teaches deep learning CS230 with me on campus at Stanford, and he's also CEO of Workera. But so Kian really likes iguanas, so he and Christian Bartholomew came with this example. So let's say you give labelers instructions to draw bounding boxes around iguanas. So well, some labelers will draw this bounding box. Different labeler will draw bounding box like this, right? 2 bounding boxes, so you have 2 iguanas. Another labeler will draw bounding boxes like this. And so I find that there's a lot of inconsistency in how labelers will label things unless you drive to very clear data definitions. And this is true for, well, labeling iguanas is a made-up example, but I see this all the time in manufacturing. I see this all the time in healthcare, where even 2 doctors don't agree on the right label. And I see this in speech recognition, agriculture, and other domains as well. And I feel like we've used the concept of human level performance to improve AI. And what I see is there's some AI teams that measure human level performance, and then they will go and say, hey, my AI system outperforms human level performance. Therefore, I have proven that my AI system is better than humans, and thus you must use it, right? And I find that whereas human level performance is a very useful development tool, is a very useful benchmark, it's great for publishing papers, I find that in a practical deployment context, the exercise of proving we're superior to humans, that's often not like that's actually not the right approach, because ultimately what we want in a healthcare setting is not just superiority to humans. We want to solve a problem and diagnose accurately if a patient has a certain condition or not. So I think that there's actually time to rethink how we benchmark and how we use human level performance in building AI systems. We'll chat more about that later as well. So just a couple more slides, then just a few more slides, and I'll wrap up. I find that one of the things I'm still trying to get better at is scoping useful problems to work or to solve. And so, I find that when AI is very interdisciplinary, right? I find that AI by itself is totally useless. What was AI for? AI has to be applied to some important application or some useful application for it to create value. So when I meet with my healthcare friends, or when I meet with business leaders, in manufacturing, in telco, in agriculture, I usually tell them, don't tell me about your AI problems. I don't hear about your AI problems. Tell me about your healthcare problems, or your business problems, or your telco problems, or your manufacturing problems, whatever. And it is my job to work with you to see if there's an AI solution. But so my common workflow is to learn about my collaborators' business problems, and then to work together to brainstorm AI solutions. I think there's certain set of things that AI can do, certain set of things that are valuable for business. And when I use the term business, I mean in a very generic way. I mean also, for a collaborative research lab, or for a nonprofit, or for a government entity, right? But we want to select projects at the intersection of these two sets. Only AI experts today have a really good sense of what's in the set on the left, and only domain experts have a really good sense of what's in the set on the right. And so I tend to go to partners that are domain experts, ask them to tell me about their problems, and then brainstorm solutions. And I think also, the process of diligence on value and feasibility and resourcing and milestone. So these are all important parts of the scoping process. So just wrap up, I drew this picture as clearly highly iterative process, where sometimes you go from the later stages to the early stages. Building models is a focus of a lot of AI research, which is great because that's made a lot of progress there. But I feel that for AI to reach its full potential, especially outside the consumer internet industry, which is maybe the one industry that's gotten really good at this, I think there's a lot we need to do to get better at the cross-functional brainstorming to pick projects, the data acquisition, as well as the deployment technologies and processes. Wanted to end with just two more slides. McKinsey had a study estimating $13 trillion worth of value creation through AI, which sounds like a lot. It is a lot. But the most interesting thing to me about their study was showing that this untapped opportunity may lie outside the consumer internet industry, that the amount we could do to help people all around the world in all of these other industries, from retail to travel to transportation to various forms of manufacturing to healthcare to other industries, maybe even bigger than what we've seen in the consumer internet tech industry so far. But to realize that value, we need better research and better engineering in order to make that happen. To summarize, much work in industries outside consumer internet still needs to be done to bridge the proof of concept to production gap. Some of the key challenges are small data, generalizability, and robustness in change management. And I think we should think more systematically about the full cycle machine learning projects. Today in our intro to programming class, CS 101 or CS 106, right? Stanford has wonderful lectures like Mehran Sahami and others that teach undergrads how to debug software. And I think we as an industry have turned software industry increasingly into systematic engineering discipline, where we can now relatively accurately predict what a software engineering team can and cannot do. I think machine learning is still too much of a black art, where there are people of experience that can get it to work for some strange reason. But why is it? But I think that we together, academia and industry, should work to turn machine learning from this black art, intuition, skill-based discipline into systematic engineering discipline. And it's only if we do that, we need to develop the processes and then also teach people the processes, then that will be a big step in breaking open AI into many other industries. So with that, let me say, thank you very much. And I'm looking forward to taking some of the questions on Slido as well. So thank you.
Thank you so much, Andrew. Thank you for the wonderful talk. There's some really interesting questions in Slido. But first, I have a burning question for you, which is when you're working on the ChexNet problem of chest X-ray diagnosis, you can write down an objective function. It's a supervised classification problem. You can build an algorithm. You can go off and do it. But at the end of the day, you have a radiologist that's trying to make a diagnosis. You have an algorithm that's trying to make a diagnosis. On the one hand, you could try to make a decision just based off of the algorithm. On the other hand, you could just have the physician make the diagnosis. And then there's a whole spectrum in between. How might you systematically study what that right human interaction is with that predictive model? And how do you handle accountability if a decision goes awry between man and machine, person and machine?
Yeah, right. Great question. I think the short and simple answer is complicated. So I think, there are different groups, including at Stanford, Pranav Rajpekar, Jeremy Irvin, Matt Lundgren, Kurt Langlis, many teams developing UIs to enable this human-machine interaction. And what we've found, for example, is that if the UI is poorly designed, we could unfortunately influence doctors to think to just go with the AI decision. So we're actually designing UIs to try to let the AI convey to the physician that we don't really know. We think it's like 70% chance, but so that's actually not very certain. So please take a careful look and figure it out yourself. So that UI design was complicated and still evolving. And I think also one thing I'd love to see rise in AI is auditing. And I feel like, who wants someone to audit my code? They just trust me, it works, right? But I think that's actually the wrong attitude, because for these systems to be deployed safely, we do need to build trust. And sometimes I look at the systems that my teams built and I look and go, gee, do I want to trust this myself? And I would appreciate a third party not to audit my work in a negative way, but to just help me spot problems so that I don't deploy a system and then find out much later it has some really undesirable, bias or some other problems. So I think the AI community should welcome auditors to have third parties help us find problems in our own work proactively, so we don't deploy a system, which we've seen, right? Systems deployed figure out is really biased against some ethnicity or some gender. So I think that would be an important step as well.
Yeah, I completely agree. And sort of a related question here is something you said earlier in your talk, where the doctors at some point, they didn't need an AI explainability tool. What they just wanted was the ability to build trust in that system. So is there a way to sort of study that systematically? Like you mentioned a UI, but are there kind of best practices for allowing a human that's interacting with an AI system to sort of build trust in a collaborative relationship?
Yeah, so I think one of the reasons the explainable AI field, it sounds so complicated, is because when people talk about explainable AI, sometimes all the different use cases get mushed together, and I don't think it's possible, at least I don't know how, to build one technology, one visualization tool, whatever, that simultaneously serves the purpose of explaining to a machine learning engineer what's wrong and thus how they can iterate to improve the algorithm, and also explains to an end user why the AI system generated this conclusion and why we hope they're comfortable with it, and also show a doctor, a subject matter expert, why an AI system generated the conclusion, but we want them to understand what we did, but also intervene and actually think about it. So those are really different purposes, as well as regulators is another stakeholder. So the fact that the machine learning algorithms are so different and the stakeholders are so different, and we hope the stakeholders to take very different actions, ranging from, be comfortable with it. If a loan making algorithm either accepts or someone rejects someone for a loan, maybe there's an appeal process. For a lot of time, we just want them to understand the decision, maybe appeal it, but most of the time, kind of just understand so I don't think it's possible. I certainly don't know how to build one technology. And I think that if we could clearly separate out the stakeholders and the purpose for explainable AI, then we can build more distinct tools for these different groups.
Yeah, got it. These are all sort of tough things at the heart of human-centered AI, which is what HAI is all about. So if I may switch.
Just one thing. I feel like I really welcome the input of sociologists, because I think a lot of the problems we face is you know, I love getting economists and sociologists and other stakeholders to help me think through how do we deal with these things that aren't a pure technology problem, but where the algorithms we develop can have a big role to help as well.
So here's a question from an economist, actually, and I'll just read it verbatim because it's really well written. What do you see as the best way to address challenges of growing inequities, especially economic inequality that AI may bring? Not an easy question, but I think a good starting point.
Yeah. Oh, cool. Oh, actually, I see it's from Eric Brynolfsson. Hey, Eric. Great to see you here. Really enjoy interactions with Eric and reading his many books over the years. So actually, those of you, if you're looking for good books on AI and economics, check out Eric Brynolfsson's books. It's nice to hear. I think one of the unfortunate things about AI, which I think Eric is alluding to, is I hate to say it, but I think AI is and will has a risk of accelerating economic inequality, right? Just the very high level pattern is, let's see, you know, once upon a time here in the United States, you could be a small scale chicken farmer and, you know, have a pretty nice life farming chickens and selling chickens and selling eggs. But now with first of the internet, a centralized player, you know, say Tyson Chicken, I have no relationship with them, right, can now use IoT to get sensors from all around the country on what's going on, centralize the data using the internet to headquarters of one data center, use AI to process the data in a centralized way, and then push conclusions of IP or technology back out to all of these farmers potentially. And so what we've seen already is in the software internet world, there is a winner take most or winner take all dynamics. So that's why there's a relatively small handful of leading web search engines and relatively small handful of leading social media companies. And because tech has now infected every industry, fortunately or unfortunately, we are infecting almost every industry from agriculture to manufacturing to retail to logistics with more and more of the winner take all type of dynamics. And this is contributing to inequality, unfortunately. I wish I knew how to address this. I think that government needs to play a huge role in this to ensure that we're going to create tremendous wealth. That's clear. Have already done so. You know, as a community, we're going to do so. I'd love to see government, and actually Eric and I were chatting a lot about ideas like unconditional basic income or even conditional basic income to give people a safety net. And then I think education is still not a panacea, but a very powerful tool to make sure that people whose livelihoods are disrupted, you know, have a chance to learn more and contribute to the economy and earn a livelihood for themselves and their families. I feel like as an AI technologist, I have seen AI create tremendous value, but I hope to all of us on this call, you know, that when you're in a hot seat to make a decision, do try to make a decision to bias things toward making sure that the wealth we create is fairly shared.
Yeah, I completely agree. And I think that's a nice segue to another question that sort of bubbled up to the top, you know, about the role of sort of industry versus academia and sort of a have and have-nots, right? So in industry, you have access, you might, if at a consumer internet-based company, right, you have access to more data and more compute. So you can do things like OpenAI can partner with Microsoft to build things like GPT-3 that, for example, academics and other people without those resources cannot. So this is, of course, a cutting edge algorithm. And for now, there's an inequity here. And, you know, the question here is like, what effect do you think that this impact will have on society? And will we see an even playing field in the future? Like, how should we all think about that?
You know, I feel like the future is not yet determined, and it is up to all of us. What we saw in the semiconductor industry, you know, making microprocessors is the center of gravity has shifted significantly from academia to corporations, because most universities just don't have the process, just don't have the resources to design and take a new semiconductor chip to fab. And so a lot of the influence is now concentrated in a few great companies like NVIDIA, Intel, AMD, right, and a few others. I think AI has made some of that shift, where today there is some work that is much easier to do in a corporate setting than an academic setting. On the flip side, there's still plenty of stuff to do in academia. And I think that, there's plenty of stuff. When I look at all of the amazing research that goes on across HAI and across Stanford and across academia, I think if you look at the papers, say, at top conferences, right, ICML, NeurIPS, iClear, and so on, it is true that large corporates has a growing share, and that's great, because I'm really glad that the large corporates are spending resources doing research and sharing the results with us. That's great. But universities also has plenty of great research as well, and so do much smaller companies. So I think, I think one thing I love about the AI community is it feels to me that the AI community grew up with a genuine spirit of sharing. And I think we as a community, all of us, any of you, if any of you listening to this work for a large corporation, you have a voice and your work matters. Go ahead and try to influence your large corporation to stay true to the spirit of sharing ideas, because it's only by doing that we could create more value for everyone. So I think the future is actually not set. And I think the values of all of us as a community will have a big influence on whether there continues to be very diversified, very widespread research with ideas fairly shared, or ends up being more concentrated. I am an optimist. I think we're actually on a good path, but it is up to us to keep pushing in that direction.
Well, I do agree.
Sorry, and of course, we all know that yesterday's supercomputers is today's smart wall.
I think my Zoom crashed. All right, we're back. So yeah, I tend to agree with you that the future is not set, but like as of now, at least for like the best performing large language model, at least in sort of a few shot task, right? Everyone that's not OpenAI is sort of stuck licensing the technology. And, I can see a way in which we move towards a more equitable version of the distribution of that technology. But let's say we were to be stuck in that, like what would be the right way? Is this like a good thing, a bad thing? Like how should we think about it in the present?
I think it would be a terrible thing if everyone, if everyone had to license GPT-3 like technology from a single provider. But again, lots of credit to the OpenAI team for building that. Fortunately, I think there are multiple companies on the planet with the capability to replicate that. So I would certainly, welcome, right, more large companies to build these things to make sure that there's healthy competition. It is an unfortunate dynamic of AI that there is this, we create a lot of value, but we also accelerate this winner-takes-all dynamic that I alluded to. It's possible that eventually we need to make sure that we have good regulatory frameworks to ensure that we have the societal effects that we want. Although for now, if you look at cloud computing, there's a relatively small number of cloud providers. So that I'm not saying that's not a problem. Fortunately, it's remained relatively competitive, but this is something that I think government should play a role to make sure that we as a society get to the outcomes that we want.
Okay, well, there's 1 minute left, so I'll try to sneak this one in quickly. What do you think are the challenges for privacy preserving machine learning in the healthcare industry? And what do you think needs to be pushed forward the most in that area?
I feel like the one challenge we have in privacy, certainly bias and other things, is we've not yet come to agree on what is the standard we want to stick to. And this has two effects, both bad. One, an AI team will build something, and as far as they know, they're doing okay, and then deploy it. And then, 2 years later, some new standard arises. Like, I think we all know there's certain protected characters we should not discriminate against. But when actually, here's a concrete example. I went to a major web search engine, image search engine, and I was searching deliberately for image search queries that would show gender bias. It took me about 10 minutes to find one. But on one of the major image search engines, eventually I figured out, I think I found elected official person. That search query on one of the major search engines showed all men on the first page. Now, so we could get sensationalists upset about this because it was biased. It's horrible. How if my 19-month-old daughter Nova, if she sees this, maybe she'll think, wow, elected official should be all men. Maybe she should never aspire to an elected official. So we could get alarmists about this. The other side of the story is it actually took me 10 minutes to find highly biased queries, so probably it won't affect Nova that much. One of the problems with these is that a lot of these issues of bias, privacy, they're statistical concepts, and we as a society need to get better at not, latching on to anecdotal evidence and to measure these in a statistical way. Because I think, I'm not going to name the search engine because I think on average, the team actually did a great job, and on average, their queries are relatively fair. And I think part of what we need to do, both business, corporate regulators, is establish fair standards to clearly lay out what we want and don't want. And then also to rigorously audit the systems against established criteria. And this will help two things. One, it diminishes on the research and engineering side the fear that I'm going to roll out something, and then 2 years later, there'll be some new thing that I just never thought of. Hey, who would have thought that I can't discriminate? Some new criteria. Like maybe you figure out we're discriminating against people that live in my hometown of Los Altos, and is that okay or not? Sounds like it's not okay. But if we establish clear criteria and then audit, then it makes life easier for the engineers and researchers. And it also, when we roll these things out, gives us a sense of what are exactly the privacy standards and the fairness standards we want the systems to adhere to. But until we get there, I think we end up with just more confusion and people getting surprise criticism, which isn't the goal. The goal is to make the systems fair, not to randomly make people feel bad about the system. So I hope we can get there.
I tend to agree with you. Well, we're a little over time. So with that, I just really want to thank you for coming and kicking us our inaugural HAI Research Seminar Series. And thank you to the community for tuning in. The recorded seminar will be posted on YouTube by the end of this week. And next week, same time, same place, we'll have Percy Liang discussing semantic parsing for natural language interfaces. So you can check that on our website. And thank you so much again, Andrew.
Yeah,
Thank you, Andrew.
Thank you.
Fantastic. Thank you.
Thanks, everyone.